Now that we know the rules, let's summarize and give you a chance to practice using those rules. So our n is defining the shell or the energy. So this corresponds to the lowest number it can be as 1, 2, or 3. When we go to L, this is defining the subshell, and the number of L values tells me the number of subshells there are. So for n equals 1, L would equal 0 through n minus 1. So we start at 0, and then we go to n minus 1. Well, 1 minus 1 is 0, so the only possible value for L is 0 here. So that tells me that I have one subshell in the n level. When I go to m sub L, this tells me about the specific orbital. And the number of m sub L values tells me the number of orbitals that are present in that specific subshell. So m sub L ranges from minus L to plus L, including 0. So the only value here is 0. So I have one orbital in the s subshell in the n equals 1 shell. So there's one orbital total. We call this orbital the 1s orbital, and there is only one orbital in the n equals 1 shell. And let's clarify that I'm talking about in the shell total number of orbitals. Now in n equals 2, L can equal 0 or 1. So let me put another line in my table here. When L equals 0, m sub L equals 0. So that is my s orbital. We call this the 2s orbital, and there is one of those type. The L equal 1 subshell would give me values of minus 1, 0, and plus 1. So there are 3 p orbitals within the n equals 2 shell, and these are called the 2p orbital. There are 3 of them of that type. So total orbitals I would have 4, and here I just have 1. Now I'd like you to take a moment and try to fill out the numbers for the n equals 3 shell. When n equals 3, we will have 3 possible L values, 0, 1, and 2, ranging from 0 to n minus 1. So we'll start here with 0, 1, and 2. And I'll draw some additional lines in my table for clarity. So when L equals 0, m sub L is going to be 0 as well. So my quantum number for this 3s orbital would be 3, 0, 0. And there is one 3s orbital in the third subshell. When L equals 1, this corresponds to my p subshell. And there are going to be 3 values for this subshell, as usual, right? You're starting to see a pattern, I hope. This would correspond to my 3p orbitals, and there are 3 of them. So far we have 4 total orbitals in my third shell. When I get up to L equals 2, my d subshell, I have a range starting at minus 2, increasing through to plus 2. And that gives me 5 values for m sub L. So this tells me that there are 5 orbitals in that d subshell. And there will always be 5 orbitals in the d subshell. Just like there will always be 3 orbitals in the p subshell and 1 orbital in the s subshell. This would be denoted as the 3d subshell, and as we said, each one of the m sub L values denotes an individual orbital in that street, in that city, right? So there are 5 orbitals total. So in my third subshell, I have a total number of 9 orbitals that can hold electrons. So the number of electrons increases as we increase the n level because the number of orbitals is increasing as well. So thinking about looking at any given shell, or subshell, we should be able to assign possible quantum numbers to that subshell. Let's say we're looking at the 4D subshell. Well, we can assign quantum numbers. N would equal 4, that's my principal quantum number. L corresponds to the D, that translates to the number 2. And then M sub L, there are actually going to be 5 possible answers to M sub L, ranging from minus L through to plus L. And any one of those 5 is an appropriate notation for one orbital within the 4D subshell. We also have to know that we can't break any of these rules. So for example, when n equals 1, L could not equal 2, okay, because L ranges from 0 to n minus 1. Likewise, when n equals 2 and L equals 1, M sub L could not equal plus 2, because again, M sub L ranges from minus L to plus L, including 0. This does not fall within that range. So these are not valid sets of quantum numbers. Keep the rules in mind as you're working on problems and assigning these values to different orbitals and electrons. Thanks for watching.